Namaste, Namaskar. Today I'm going to start a new topic. It's regarding stability, but it is not the basic stability, it is related to advanced stability. When I say advanced stability, it is part of your MATE syllabus. You can see uh, this usually is a syllabus for your MATES Phase 2, which is the DG syllabus in India. And I'm going to talk about SF and BM for BEAM. And when I say this syllabus is for MATES Phase 2, you should realize that it is there in the BSc also, the 3-year BSc program. So that is why I have tried to make it as simple as possible so that the BSc students who have still not started sailing also understand the concept first, and then we can look into solution of a problem. So right now my aim is to talk about concepts. So the part 1 of this series will talk only about the concept. So let us look at this topic, and let me start with the foundation. Let us understand the whole idea of what is this SF and BM. And before I start, I'm going to just again quickly recap on a little bit of basic stability also. Now, the title what I gave you is SFBM of a beam. So we can consider the length of the ship. If we don't take it as exactly ship shape, it is equivalent to a length of a beam or a log. You can consider that for the basic studies and understanding. So I've just shown you a ship shape on the side view, which is longitudinal side view. And this is also a log, or I can call it beam. Most of the questions, the basic question starts with the right side picture. This is how majority of the questions will be there. Okay. Now let us understand or quickly recap few things right from the basics. So when a ship is floating, you should agree that the total weight of the ship will be equal to the total buoyancy, and both acting opposite to each other, which means that the total weight, which is also a force, should be equal to the total force of buoyancy also. So that is how a object will float. Now let me take quickly shape of a ship, and I've divided them into various holds or compartments. Now one of the most important thing you should agree is, even though the total weight is assumed to be acting from a single point called center of gravity, which is also called a centroid of weights, geometric center of weights, I can show you, let us say, assume that this vessel had the COG at this place and it will be vertically acting downwards. But there is something else you should realize. The position or the location of the COG, which is kind of a virtual point, actually depends on the distribution of weights in these holds and the ship rather than your total weight. So assume I had some cargo here like this, uneven distributions. So each hold or the compartment will have its own center of gravity depending on the cargo. This is how the actual ship will look. Now at the same time, I need to talk about the buoyancy also. Buoyancy is also a force. So that is also assumed to be acting from a point called center of buoyancy, which is again the geometric center or centroid of the underwater volume. Now this buoyancy also has got a similar results as what we talked about center of gravity. Let me just show you a single point, which is your center of buoyancy. This is how normally center of buoyancy would act. But as I said, this is also similar to center of gravity, which means the position of the center of buoyancy depends on the shape or the distribution of the underwater volume, how the underwater volume has been distributed all along. Okay? It is not on the total buoyancy. Your ship shape is not symmetrical. We all know it is not same as in when we go along the length, right from, let us say, from forward to aft. So I can just show you an approximate three-dimensional diagram of a vessel. This will approximately look like this, and you will have a draft and underwater volume, and the buoyancy, center of buoyancy might act from here, but please remember the underwater volume distribution along the length is not the same. So that means there will be uneven distribution of your underwater. Now weights are acting downwards from a lot of points, just like the way I showed you in that compartment, different compartment. They're acting from all different points, and they're not the same. They're not the same, and they're not just from one point. Okay, since I already said ship shape is not symmetrical in all the places. Okay. And your center of buoyancy depends on distribution of underwater. So that means gravity depends on distribution of weights, and buoyancy depends on distribution of underwater. Okay. So it need not be same, just like the way I showed you the previous three-dimensional diagram. It is not same. Why? Because the forward part was a triangular part, the midship was a rectangular part, the stern was a semicircular kind of physical part of your ship. So it is not same. So buoyancy distribution is also not same. Now your vessel can be trimmed or listed also. So I've just shown you a trimmed vessel, trimmed by stern. But the problem is, please look at the underwater volume distribution here. I'll just go back to the previous slide once again. If you look only at the gravity, this is what was the gravity. Please remember the cargo I have shown you is still the same. But obviously, even if it is trimmed or listed also, the force of gravity is still going to act vertically downwards. Now, I'm including the water now. So all I've done is I've included the water, which means your draft. The drafts is not the same in the forward and aft, which means the force of buoyancy is also not the same along the length. So they are different. This is what you need to understand. Now, this creates a small problem. So before I go to that, let us just say what is perfect condition. If the weights, all the weights in the holds are exactly same, then you might have all the force of gravity is also exactly the same. And let us say you have exact similar distribution of underwater volume. That means force of buoyancy also will be exactly same all along the length. So they will cancel each other, but this is not common in a ship shape. This is possible on a pure rectangular type of vessel, which is not practical. Which is not practical. Okay. So this is what you need to understand, that they are not perfect. Now this concept is applicable for a ship also, a log also, a beam also, whatever it is. Now I've just shown you a case of an alternate hold loading. Okay, this is just to depict you, tell you how the forces are going to act. Now look at that alternate holds where cargo is there. You will see the weights are maximum acting from there. Even though the empty hold also has got its body weight, but it's very, very minimal compared to the full hold. Now similarly, I've shown you the force of buoyancy acting quite strongly at the empty holds. Even though in the filled holds also, on the underwater volume which the filled holes have outside, they also have force of buoyancy. But you will see they will act more on this empty space. Why? Because there's nothing to cancel here. Now this is the problem where you might see it will create uneven weights and buoyancy, hence it will start stressing the ship. Stress is a force. And in this particular case, which is a hypothetical case, you will see the bulkheads which are joining the full and empty compartment. They will have a lot of force coming on them. I have marked with these red color spots where you will have a lot of stresses. Now these stresses, please remember, can damage also, or in a long term can create deformation of the vessel. Okay. So that is the reason I need to know these stresses. So when I want to know these stresses, it is depicted in two ways, and that is what is SF and BM, which we are going to look at. Okay. Before I go into the definition or the explanation of SF and BM, let us quickly look at a few common structures which are possible to you on board also. And if you ask me, they are possible at home also. Let us quickly look at it. Not necessarily at home, it will be on the land also, anywhere near your house also. This is what is called simply supported, okay, which means that I have two supports at the extreme ends of a beam or a ship or whatever you want to call it. This is simply supported, okay, just simply supported. That means you are supported at the ends. Now I have something called overhanging. You will see the supports will come little bit inwards for the same beam, and they are not at the ends, so it is called overhanging because the ends are over. And the last one, which is very common for you in exams and even in your common day-to-day life, is cantilever. Cantilever is somewhat looking like this. It is supported at one and the other side is free. Now, whenever a load is applied to a beam, let us say you put a weight or it has got its own weight, it bends. Please remember it bends. So I've shown you a simply supported beam and you try to put a force on the middle, it will bend. Now what happens is the upper part it's compressing, becomes shorter, the lower part tries to elongate and becomes longer. But the middle part, please remember exactly middle part is called neutral axis. And this neutral axis has to be strong for that particular beam to survive for a long time, these stresses. Now, beam normally, when you take off the load, will regain its shape back, will come back to its original shape. But if you go beyond its elastic limit, you should realize that there could be a permanent deformation. That means it cannot come back. There's something again, elasticity of your subject in the physics, what we have learned in the schools also. Now let us look at this first force called shear force. Okay? What is a shear force? It is nothing but a force which tends to tear apart the beam. Okay? Tear apart the beam. The beam is that structure perpendicular to this major axis. So let me show you a small diagram. In other words, the shear will try to shear or break the beam across. So when I say break the beam across, it'll try to even slide one layer over the adjacent layer and try to separate it. So I've shown you a diagram with three different forces. I'm not interested in all of them. I'm interested only in the shear force. So please look at the last on the left side. So you can see if I give you a major axis, this shear force is trying to tear it apart perpendicular to that. Just a depiction, just to make you understand. Similarly, you can see here, it is trying to slide one layer over the adjacent layer, again perpendicular to the major axis. So this is how you can explain what is shear force. When a beam is in static equilibrium, that means nothing has gone wrong, it has not got damaged, and if I remove the forces which is acting on it, it will come back to its own shape. In this condition, which is called static equilibrium, I'm not putting any dynamic forces also, your net resultant of all the forces which is acting on that particular beam should be zero, which actually means, I can put it in a different way, that means at any point, your algebraic sum of forces acting on any one side, that is how this whole calculation of your SF and BM are done. We'll always say that, let us say I have one frame and I'm asking you what is SF on this frame. We'll always try to take the algebraic sum of all the forces to one side, and we always try to take the left side as a convention. You can all do a right side also, but as far as the system we follow, we are always using the left side. We'll take the left side. Okay, let us quickly look at the convention of your SF. SF also is given a sign convention. All upward forces are called positive forces and all downward forces are called negative forces. I'm just trying to show you in the picture. All upward forces are called positive, downwards is called negative. Whenever SF uh, encounters a sudden change in force, let us say the same example which I showed you in that alternate loading, you can see a sudden change in force. That means one tank was full, other tank was empty. At that frame, you will see a very sudden change of shear force, and that is where it tries to stress maximum. Okay, so this happens wherever your weight and buoyancy are suddenly changing. There is this encountering of sudden change, which is also called as point load. So I'll talk about this later when we start solving questions. Now let me come to this bending moment. I'm going to show you a diagram. I've drawn a few arrows already because to avoid your animation. Now, bending moment is nothing but a measure of bending effect due to this force which was acting. Which force? It is the shear force. And how is it represented? It is given as the force multiplied by the distance. So it is a moment. Moment is always something multiplied by a distance. Okay. Now, BM at any point on the beam is the total moment which is tending to change the shape of the beam. It will try to change the shape. One of the pictures I had already shown you. In other words, it will try to bend the beam. So this is the same picture which I had already seen. Now what happens is you are applying a force and that force is trying to bend the beam. This is what is your bending moment. How you calculate? If you go to a point, I'm going to take the force into a lever. That is what I'm doing. And exactly like before I said, this it compresses the top part and stretches the bottom part. Again, whenever a beam is in static equilibrium, it's exactly the same as I told you in SF. You have to tell in a kind of mathematical way, and they say sum of all clockwise moments about any point is equal to sum of all anti-clockwise moments. Okay. So, in other words, the algebraic sum of all the moments acting on one side, which is uh, that is how you calculate your bending moment. You stand at a frame, you calculate algebraic sum of all the bending moments on one side, and here also we take the left side. Okay, we take the left side. Now, let me show you a small picture. Let us define again the first para. When I said whenever you have a static equilibrium, the sum of all clockwise moments about any point is equal to sum of all anti-clockwise. So, which means that I am trying to talk about a kind of sign convention for your BM also. So, let us look at the sign conventions of BM. You please see here, positive sign for BM means clockwise movements to the left and anti-clockwise movements to the right of a chosen point. So I've shown you your clockwise on the left, anti-clockwise on the right. Okay. In other words, BM that tend to cause a beam to sag are called positive, which means you can see this left side is sagging. Okay. You can see on the right side picture also, I am showing you a sagging picture where it is positive. Now, what is negative? Negative is exactly opposite. I'm going to give anti-clockwise on the left side and clockwise moments on the right side, which is again telling you that this will create a hog. So that is why on the right side picture, I've shown you a hogging vessel as a negative sign convention. These sign conventions help you in calculations. Okay, should you use it? Yes, because it will help you to calculate very easily. Otherwise, if you don't put it and start calling it positive and negative, but just by word of mouth, it creates a lot of hassle. So we will stick on to the sign convention also. Now, the only one thing I would like to add is both of them. I have mentioned one thing: static equilibrium, static equilibrium. Your shear force when something is in static equilibrium, you will see algebraic sum of all the forces will become zero. Similarly, when again it is in static equilibrium, the BM also, when you do a summation of all the clockwise moment, anti-clockwise, it will become zero. And that what means that any beam or a vessel is in static equilibrium. I've just shown you again the signs of shear force and bending. If you translate this to a vessel, Please see here. There are two forces, important forces happening on a vessel. One is weight, which is creating downward force, which is negative. There is something buoyancy, which creates an upside force, which is positive. And because of this, I'm getting a shear force and bending moment depending on the distribution. Please remember that is what is most important. Okay, that's the end of this first video, which talks about the concepts. I hope it was helpful. It will be helpful. Why? Because when you start solving problem, you need to remember all these sign conventions and the meaning and how to calculate. So I'll stop this video here, and I'll come back with the next series of this. And I'll have to talk a little bit more about a few formulas, how to start the question, and then I will start the question. Until then, keep watching and hope you have learned something. Vanakkam, namaste, namaskar.